Good afternoon. Good afternoon, Isabella. Hello, Ray. Hello. Oh, I missed. Wait, sorry. Hello. Thank you. Wait. Good afternoon, Cynthia. Thank you, Ardell. And I want to address that. Thank you. Yes, I very much radio silenced. But thank you. Hello, Brian. And someone's coming in. Sorry. And oh, wait, can you hear me? Yes, you can. Good. Thank you, Amanda. He's doing good, or he's doing well. Thank you. I will address that and say, very nice of you to remember. He totally does not have COVID. If anybody was, but yes, thank you. And I would good. Thank you very much. That is very nice, Farina. Good afternoon to you. I appreciate it. You guys are very classy individuals. I wish my kid were brought up half as well as you were brought up. But he's got major DNA disadvantages to fight. Okay, wait. Hello. Coming on here. Okay. We're starting in a second. Oh. Okay. Things are happening electronically. We're going to start in a second. Well, we are starting. One thing. Please bear with me for a second because I totally did, in fact, neglect to do. And if someone's in the waiting, bear with me. I think someone is in the waiting room, but I can't get them for a second. If they text you in panic, please ask them to stand by for a second. Yes. Please continue to bear with me for us. Okay. Bear with me for a I always say, wait a second to my kid, the kid who was sick, and thank you for asking. I always say, wait a second, and now he's just old enough to get all obnoxious when I say, wait a second. He goes, you mean a minute, don't you, Dad? It's not going to be a second, right? It's going to be a minute. Like, okay, yeah, fair enough. Good point. So bear with me for a minute, please. Oh, no, I did it wrong again. And of course now, but really why I say, wait a second is, of course, when I say wait a second, I really mean wait a minute. But if I were to say wait a minute, then it's going to be an hour is the problem. I mean, whether it's him or you. So so what am I trying to do? So I'm okay. Okay. First of all, so I do owe you, all of you, a couple of apologies. I mean, not that you care about apologies, but a couple things to address or acknowledge. Right. First of all, so I did cancel class last Wednesday, and yes, it was because my kid is sick. He doesn't have COVID or anything like that, and he is fine. And it's more just that when people are sick these days, it causes major ripple effects and inconveniences, blah, blah, blah. But thank you for your concern, and everything is fine. But I did cancel class. Wait, I did cancel class, but then here, and I apologize for that. But then also, I just want to make clear that then I said something like, I will be posting the material, in some video form or something. Look out for this weekend, look out for something that I will post to compensate for the material. And then I totally did not post anything. I just wanted to, first of all, if you were wondering, or if you think you're confused, or if you look for it and you think you can't find it, no, it is me, not you. There was nothing posted weekend. So that's the fact that is bad. As far as the material itself, I will still compensate one way or another. We will get to everything we need to get to. You will be educated to the extent that you ever would with me. But I apologize for the fact that that we did miss material for the moment. And I definitely apologize if I caused any anxiety or confusion if you were looking or waiting or thinking. It's totally my bad that I did not. It was a crazy week. No problem. Thank you very much. I see you. Yes, I see you. And thank you. All good. I'm in the middle of an apology right now. So please, I can't accept any further apologies. But right. So I didn't post anything. We will make up I'm not going to make you do extra work just because I missed a class, but we will cover that curriculum one way or the other. But there's another thing I wanted to apologize. Oh, but also because, yes, he did continue to be, it was a crazy weekend. So also I didn't grade anything. So just to be clear, like if last you heard from me on that, no, let me back up. Test corrections were technically due last Wednesday or something, or last Monday, and anybody who did turn them in, I did see that, and that is awesome. And I think some people actually did really take them seriously and do a good job. I have not graded them, but I do have them, and I see that you did them, and thank you. Those of you who did not do test corrections yet, who you still can. Okay, I'll update the thing in the classroom, but don't. That's like a normal homework assignment in that we're all have soft, fuzzy relationships with the clock right now, except when it comes to actual exams themselves. So if you're still wishing to do test corrections, you still can. And similarly, and anything else you've done in the past, if you're wondering whether I did not grade this weekend, so I still may owe you other things from the past. But lastly, that funny assignment I made up about where you're going to redo a problem with a partner, blah, blah. If you've turned it in, I have not graded it yet. I still will. If you're waiting on me to set you up with a partner, I'm sorry, this is dragging along like this and all that, but the ball's in my court, not yours, is what I'm saying. So there's just a global apology for right now. I'm definitely behind you guys, not the other way around. And even though I do with our limited time left as a class, I still do want to catch up and move maybe somewhat quickly through some curricular material, but you're not going to have any extra homework tonight or anything like that to, until I catch up. And so whatever back things you still owe me, you can do. All right. So anyway, I guess I'm saying welcome back to myself and saying I'm now here today to catch up with you. Okay. Right. Okay. But we are going to go on with the curriculum today. We're going to go on with what we were doing last Monday. In other words, we're going to go back more to wave discussion. I know you're in the midst of talking about Doppler effect in the lab. I want what we do in lecture to correspond to that. So we have to do we are going to do a derivation or a proof today that is thick and super important. It's super pivotal. It's mathematical in nature, very mathematical actually, once we get rolling with it. It used to be such a big deal in this class. Like I used to take 2 or 3 days on this one proof, and we used to have a separate exam just on this proof. Just to put in perspective, that's not going to happen in this class. We're not going to have a separate exam on it, but it is kind of a big thing. It's about, and I'll explain it, of course, in a minute, but we're probably going to do a lot of setting it up today. Like we're going to do a lot of setting it up today, and we probably will do very little of actually going through it. We'll probably do the rest of going through it on Wednesday. But I need to give it context. I want to give it a little context. We are going to derive something called the wave equation. You have seen a form of this wave equation in lab or in lab 3, I think, but whether you did or did not or recognize it or not, we're deriving it fresh today. We're going to analyze. So today we're going to analyze a wave pulse traveling along a string. We're going to analyze a long horizontal string with like a vertically shaped pulse propagating along it, a la lab 3. Like we're going to kind of zoom in. And again, of course, if there's any questions at any time, please ask. I mean, this is a very lecture-y kind of day. Okay. I'm going to talk a lot. You are definitely welcome to interrupt me at any time. In fact, I think there is something in the chat. I'm going to check in 1 second. So even if I sound like I'm going fast, you can slow me down for clarification or ever by asking questions. I would not, it's not a day really to go off topic or anything like that, but you almost better interrupt me. Otherwise, once I'm rolling, I'm just going to roll, and I don't, know how that feels. But for that matter, hold on, chat. Oh, funny. Well, that's okay. There's an interesting question in the private chat. I won't say the name, but in the private chat, it says on the question of waves, how do you derive the velocity of a wave? That's a great question. Because, yeah. How do I derive the velocity of the wave? That's a great question. Let me say for 2 reasons. One, yes, part of the key importance of wave motion is how reliable wave velocity is. Like, it's absolutely right to imply or to assume that the velocity of a wave is like a big deal. Also, it's very right to assume that it plays a very big role in the Doppler effect and in anything that you're doing in lab right now or anything that might be due to Professor Wu. Now, if you're asking what if that person in private chat is asking what is the equation for the velocity of a wave, well, there are actually many. One of the most straightforward equations to use, that's the one you need for the Doppler effect or that you need for lab, is V equals lambda F. That is to say, the velocity of a wave equals the wavelength of the wave times the frequency of the wave. That is one way to write the velocity of a wave. Very important way, that velocity equals wavelength times frequency. There's many other things you could say as well, but that's like the key one. And also that's the one that would come up the most in other science arenas like PChem or instrumental or and also chemistry for that matter. So if one were to be just asking what is the equation for the velocity of a wave, V equals lambda times F would be the first thing that would hop to my mind. However, this question says something deeper than that. The question in private chat says, how do you derive the velocity of a wave? And as far as deriving, that's what I want to do today. That's totally the goal of today. And it takes a while. It's a big deal. It's one of the biggest, it's a very important, but big kind of thick derivation. That's entirely what we are about to embark on today. But then the question then says, can you describe, well, and I have to be a little bit careful because this is a big enough project that I don't want to go too far afield in too many things, but, and I'm not actually also sure. I mean, and if these questions are coming because of something that's due in lab, I'm happy to try to help directly with lab, but I'm not sure if they're abstractly just curiosity questions or not. But as far as the potential energy and the kinetic energy of a wave, and actually I have a whole video about this that I made a presentation I made a while ago and it's on my YouTube channel and I can give you the link and stuff. But very quickly, if you want to know the kinetic energy of a wave, actually one straightforward thing to say is its kinetic energy is 1/2 mv squared, like it always is in classical physics. So as long as we can get the V, then you multiply by 1/2 mv squared and there you go. Getting the V is our goal of today. So these are very good questions. Yeah, no, it's cool. No, good questions in the private chat. The good news is, especially if they are just based on curiosity, great, then we're in the right place because that is totally the curiosity that I would like to address today. But it is a big project. It's no simple matter. I mean, yeah. So where we're about to head off, I mean, where we're about to go in the class today. Sorry. sorry, where we're about to go, how many ADHD professors to take the screw in a light bulb? Sorry. Where we're going to go today is we are going to derive something called the wave equation. And the wave equation contains in it is one equation that describes how waves work, and it has actually many pieces to the wave equations, and it captures many aspects of the wave. But one aspect in particular that it captures is the speed of the wave. So we're going to derive this wave equation today, or at least we're going to start deriving it today. And the way we're going to derive it, so this, and I'm just talking in abstract right now. Of course, I'm going to get out the board and everything in a minute, except, well, we're going to start writing, but there's a diagram I want us all to look at in a minute, and that's the screen I'm going to share in a minute, which will thereby mean I can't really draw for a little bit. So let me just give a quick bit of context to everybody. We are going to derive the wave equation today by analyzing a pulse traveling along a string, just like we sort of talked about last time in lecture, and just like you were supposed to be thinking about and analyzing in lab 3. In lab 3, you looked at a pulse traveling along a stretched string. In lab 4, and beyond, you're talking about the Doppler effect, i.e., you're really picturing sound waves traveling through air. I just want to make clear right now that, like, whether we're talking about a pulse on a long string or a ripple on the surface of a body of water, or we're talking about the motion of air molecules throughout, a bunch of air, which we call sound, all the underlying principles and mathematics and statements about velocity and everything else are all the same, whatever wave we're talking about. Like, once we understand waves, whichever example it is. The sort of most direct, illustrative, vivid example of a wave pulse that we can imagine really is a pulse traveling along a one-dimensional stretched string. So we are going to analyze the stretched string today. Again, we're going to be picturing essentially lab 3, but anything we say today is for the purpose of carrying over and applying to any wave that we ever encounter for the rest of our life, whether it's in this course or in another science course, whether it's a sound wave or a electric wave or a magnetic wave or a seismic wave underground, or ultimately an electromagnetic radiation wave, which is known as light. Okay, any kind of wave, if it's a wave, it's going to follow the principles and the mathematics that we say today. One just little distinction so that you know how you can make the extrapolations. One little distinction is there's two basic categories of wave pulses that we tend to make a distinction between what we call transverse pulses or transverse waves versus compression waves, compression pulses. That and this is worth writing down. I'm not writing it down now because, again, I'm going back and forth between screens in a minute. So, but please make a note that the two basic families of waves, or the two categories, are transverse versus compression, or a synonym for compression is longitudinal. Now, here's the basic distinction between transverse and compression. Again, the math is all the same. The concepts are all the same. Just the sort of mental picture or the physical setup is slightly different. In a transverse pulse or a transverse wave, sorry, I don't know what's going on with me today, but in a transverse pulse, you might even want to write this down: transverse pulse, triple equal sign, direction of propagation is perpendicular to direction of oscillation. That's a transverse pulse. I'm going to explain that in a moment, but just to say it again, and side note, the word transverse generally means across. So in this, so what we're sort of idiomatically saying here, or in general, is that a transverse pulse is one for which the propagation is across the oscillation. Transverse pulse means propagation is perpendicular to oscillation, as opposed to a compression pulse or compression wave, where for which so you could write compression pulse triple equal sign, direction of propagation is parallel to direction of oscillation. Okay, so what's the idea here? The idea again is, remember, any pulse at all, any wave pulse is a motion from point A to point B for which no individual object or particle actually undergoes the motion from A to B, right? So in the most straightforward case, like a pulse on a string, we have a long string, you're holding one end of the string, your lab partner's holding the other end of the string. We flick one edge of the string, so one edge of the string goes up and then it comes down, and then the little next bit of the string goes up and then it goes down, and then the little next bit goes up and then it goes down, and so on and so forth. So we have all these little oscillations that together, all as that each little bit of the string is just oscillating like up and down in its own little neighborhood. But the net effect of the whole phenomenon of this highly organized dance, this highly organized collective alternating staggered motion, and that's what we were analyzing last time, right? So you have a bunch of staggered oscillations, each of which is vertical, but the net effect is like this bump or this perturbation or this disturbance or this phase, whatever you want to call it, this crest, this trough, this pulse, then travels, propagates horizontally. All these oscillations are vertical, but then you see a bump on the string move horizontally. Like the only thing that is moving is pieces of string, yet the wave, sorry, let me say it again. So you see a wave pulse move horizontally, and you know the wave pulse is consisting of nothing but pieces of string. Like there's a motion that is from A to B horizontally. The only things in the world moving at all are string, yet no piece of string is moving from A to B horizontally, right? Like that's the essence of the pulse idea. And in the case of a transverse pulse, all the oscillations would be along one axis and the propagation is along another, i.e. they're across axes, so to speak. That's what a pulse on a string looks like. It's transverse. That's what ripples on the surface of water look like. They're transverse. That's what, anytime anybody draws a wiggle or tries to represent a wave somehow with drawing some wiggly, squiggly thing on a piece of paper, they're always tacitly picked. They think they're drawing a wave, but they probably got that idea of the wave either from some graph or that they're picturing tacitly a transverse wave. I just want to say, just so that you can like picture life and stuff, that sound waves, as in lab 4, as in the Doppler effect, or as in life, sound waves will follow all the mathematics and all the concepts that we're going to do today. But the truth of the matter is sound waves are actually compression waves. They're not transverse. That is, you have sound is traveling through the medium of air. You have a little bit of air molecules like moving over here, and then a little bit of air molecules moving over there, and then a little bit over there. But the air molecules, if I shout from me to you across some horizontal axis, if I'm standing here shouting and the sound is going to you, what's not happening is air molecule up, down, then air molecule up, down, then air molecule up, down. Like that could happen, but that's not what's happening. That is what would happen if it was a string that I was flicking from me to you. But if it's air molecules, what's actually happening is like air molecules are sort of pushing forward and then back. And then air molecules are pushing forward and then back. And then air molecules are pushing forward and then back. So put one other way, like if we were trying to replicate this at Yankee Stadium or something like that, like if we were trying to do a wave at like a sporting arena or like a rock concert or whatever, rock concert, how old am I? I don't know what they're called anymore. But like at a show, like a transverse wave would be me going up and then down, and then the person next to me going up and then down, and then the person up, like that's a transverse wave. And by the way, that's not like a pretend transverse wave. That's not like a as if transverse wave. That's a transverse wave. And the medium is human beings. Like if you do it right, it's a wave. And you could, send information through that just as easily as you could through phone lines, whatever. But imagine if instead of going like up, down, up, down, up, down, imagine if instead I went like this, forward, back, and then, or you know, or whatever, like left, right. And then the next person went like left, right. And I'm not saying hit the next person. I'm not saying actually exert a mechanical force or anything like that. I'm saying just shake back and forth in your little neighborhood. But instead of shaking up and down, if you imagine shaking left to right, you could still send a pulse from left to right that way, right? It's just that there, all of the oscillations would be along the same axis as the propagation. And if you think about it, if you did that at Yankee Stadium or whatever, then it's like a bunch of people getting close together and then spreading apart, and then the next bunch of people getting close together and then spreading apart, right? It would, and that's what air molecules really do, something more like that. They get tight and then loose, and then tight and then loose. So what we say, so really, it's like you have a little pressure packet of air molecules, and then they open up, and technically it's called a rarefaction. And then you have another compression, a pressure packet, a pressure zone, and then it opens up, and it's called a rarefaction. So sound waves are going to obey all of the math that we're about to do. And if you made graphs out of them, like where you put on the x-axis, you know, one axis of space, and then on the y-axis, instead of putting like y position, you put like pressure measured in newtons per square meter or something, then all the math and all the graphs would look identical. It's just I just want you to know that like a sound wave is a wave in every sense of the word. It just happens to be a compression wave. So it's more like this rather than like this. And for that matter, seismic waves, like things that cause earthquakes and stuff, like waves under the ground, those are, in fact, if you've ever heard of seismic vibration or the Richter scale or anything like that, those are, in fact, compression waves. In fact, they're just sound waves, only sound waves going through ground rather than through the air. Okay, so this is just two different mental pictures to have in mind. Again, understand that once you graph or you do the math of these mental pictures, it's all identical. Hence, so in the end, the thing we care really about is like sound waves and light waves and these other kind of unthingy sort of abstract waves. Those are the coolest. But we're going to talk about a transverse wave on a string today because it's easier to talk about, easier to draw, easier to graph, and the math will carry over to everything else. For that matter, I'm going to take a breath for a second, but for that matter, then hopefully you saw that in the Google screen. So I'm going to switch screens here. Hold on. Yes. Okay. So I just, hopefully you can see this image on the screen now. This image that's on the screen, this image file, this whatever thing, JPEG, maybe somebody can confirm or deny. This should be in your Google stream as of about 5 minutes ago. That's the thing I was futzing with 5 minutes ago. So you have this in your possession. Hopefully you can confirm or deny. And thank you. I totally appreciate it. All right, awesome. Isabella, because I'm going to spend probably the rest of this period talking about this picture. And the next period. Like we're going to prove something based on this picture. And I used to just try to draw this picture on the board, like in John Jay. And the proof is just thick enough and just important enough and just detailed enough that I've learned over time that it really hinges on the picture. When I used to draw on the board, that was bad. Like between my handwriting and people not being able to see and stuff, like there would be confusion right from the get-go. And as I said, we used to have an exam just on this proof alone. So I want you to everybody take this picture very seriously, like either have your own copy out in front of you from the stream and I'm going to have to switch, I'm not going to have it I'm not going to share this as a screen the whole time because I'm going to start writing things down. But this picture is a string that we are going to pluck, and the entire analysis that we're going to do here, the entire derivation that we're going to do is we are going to derive the wave equation from a pluck. We are just going to apply Newton's laws, like good old classical physics, to a pluck. What do I mean by a pluck? I mean, we're here going to imagine. So we're looking at this picture. We're going to imagine a long, tight string that is stretched along what we'll call the x-axis, so it's fixed at both ends. So it's like a long string that you're holding at one end and your lap partner is like way far away holding the other end, and you're holding it tight enough. Is that my hand or someone else's? Okay. You're holding it tight enough that it's tight, that there's not slack in the string. It's tight throughout. There's tension in the string, okay? And whatever direction you're holding it in normally, like with nothing else going on, we're going to call that the x-axis. Like it doesn't actually have to be horizontal. This thing, it could be the string on a cello. In other words, you could have this cello up here on a string that's like normally tied to the top of the cello and tied, and hooked in whatever at the bottom of the cello. And normally it's just straight, right? And if that's the case, we would call that the x-axis. The x-axis is whatever is the equilibrium axis for this string. So in other words, gravity is not going to come into this. We don't have to worry about gravity or anything. We're just worried that there's a string that's really long, and it has tension throughout. And what's going to happen is someone's going to come along and pluck this string. By pluck, I mean they're going to subject, excuse me for 1 second. They're going to subject this string to a displacement away from the x-axis. Like they're going to push it a little bit so the string bends a little bit and becomes a little bit disturbed, perturbed, misshapen, contorted, distorted. For the string will be pulled away from the x-axis by a very small amount, by like a small angle. It'll be a small section of the string that's pulled away from the x-axis. And we're going to pull it away from the x-axis for a small amount of time. The small segment, the small amount of time, and the small angular displacement from the x-axis, all three of those factors together combine to make what I mean by a pluck, a temporary, bounded disturbance in the otherwise horizontal alignment of this string. I'm gonna pause for a second because it looks like there's things in the chat. Hold on, and there's probably someone telling me that there's someone in the waiting room. Hold on, sorry, hold on. Oh, okay, cool. Oh no, it's you guys. Okay, thank you. Yes, so you got the picture. Great, thank you both. All three of you. Thank you. Okay, so we're gonna pluck this string. Now, realistically, like that means like there's a string. Someone comes along and just goes like kind of like you did in lab 3, but just once. Like someone just goes and they grab it and then they let it go. Or if it's a cello, someone just grabs it and lets it go. Or it's a guitar, someone grabs it and lets it go. For that little moment that they're grabbing it, hopefully you could imagine that means they pull the string away from a horizontal orientation. Oh, I see oh, that is my screen. Sorry, I see, because I'm sharing that screen. Oh, that's so weird. Hold on, how can I? You're like seeing my arm. Hang on 1 second. Okay. Someone's going to bend the string a small amount of the string, for a small amount of time. Now, I want you to, I want to make this diagram very clear and the situation very clear. So again, bear with me. You sort of have to take notes on what I'm saying, even without me writing them down. Like, we're going to assume that every time I say string, a string is a continuous medium. A string is a continuous medium, at least macroscopically it is, meaning that if I picture a long piece of string, I picture it as continuous, as infinitely divisible. I don't picture a piece of string and then a piece of string next to it and then a piece of string. Like, even though it may be true that at some microscopic and maybe even on some very important level that a string is made up of molecules that have like space between them, macroscopically, we're not seeing those spaces. We're seeing one long piece of string. That's going to become important for a number of reasons. But one of them is that if I pluck this string, if I grab a little bit of it and displace it away from horizontal orientation, well, if the string is continuous, that means that whatever little curvy shape I put in the string, like eventually that curve, the ends of the string are still fixed and the string is very long. So it's not going to act like a cartoon. If I bend a little bit of it, I'm not going to get like a jagged edge in the string. There's no way I could get like a little V or two, or the string is not going to slant and have a corner or straight lines in it anywhere. It'll have to gently slope back to where it was eventually. So I do assume that if I pluck a string, what I'm doing is turning what was a straight line into some sort of small little arc, at least for a short period of time. And that small arc is what's being depicted in this diagram here. The black curve in the diagram that hopefully you're seeing right now. In fact, sorry. No. Wait, I'm trying to get. Oh, zoom. I'm trying. Sorry. Hello. Why is this? Just bear with me for a second. All right. I don't know what you're seeing right now, but well, anyway, can you guys see the image that I'm talking about? And yeah, that's a yes. Thank you. And can you also see, and can you see my face, or can you see any faces, or can you see any people, or is it just the screen share? I'm kind of confused with it. Double yes. Okay. Thank you. Okay. So what's depicted in that picture, the black curve, is that little piece of string while sort of at the moment it's been plucked, like I grabbed it, then and now I'm releasing it. Like I'm going to release it very quickly. It's just a pluck, right? And so I let go of my fingers. So this is the moment before the string has flattened itself out again. I assume, because the string is fixed at both ends, that's the way it wants to be oriented. If nothing else were touching it, it would be oriented horizontally. So this snapshot is like the moment between that it got plucked and the moment after it got plucked, but the moment before it fully flattens itself out again. I assume it will flatten itself out again because I assume there's tension in this string, and the tension will, in a way, act or like a restoring force, kind of like in a spring, and it will. I'll get into the details of this more in a second, but I assume that the tension of the string will tighten it back to where it was before once I let go. And I assume in the meantime, this little piece of the string will be in a curved shape, but not a symmetric, like it's a curved shape, which means the slope of the string is changing every place along the string, right? Like if it were a constant slope string, then it would be a line. It might not be horizontal, it might be a diagonal line, but it would be a line. This string is curved. The fact that this string is curved means that at any 2 points that I pick of the string, those 2 points will be at slightly different slopes or slightly different steepnesses. So what's happening in the diagram here is we're excerpting this little segment of string that got plucked, and it's a little bit curvy right now at this moment. And we're sort of taking a freeze frame of it, or focusing our attention, and we picked sort of two arbitrary points that I call two arbitrary places on the x-axis that I could call x1 and x2 or something like that. But here instead, I'm going to call it x and x plus delta x, right? So I pick some point on the x-axis and then I move over a little bit, delta x. And so I've got these two x locations on the string, x and delta x. But if I imagine that this black string, this is happening in the lab in front of some big coordinate system, again, kind of like lab 3, then the axis that the string is normally oriented along is called x, and the other axis is called y. And if this string is continuous and I look at a little curve of it, the curve is some sort of continuous function, right? Like maybe that little curve is part of a parabola, maybe it's part of a hyperbola, maybe it's part of a cubic. I'm not saying I know, but there's some function that describes the shape of that string there. So instead of calling the two coordinates of these 2 points x, like x1, y1 and x2, y2, which I could, I'm assuming in my mind that y is a function of x. So I'm going to call these two arbitrary points that I isolated in the string x comma f of x and x plus delta x comma f of x plus delta x. I hope that it's just two arbitrary points that are separated a horizontal distance of delta x, and each point has an x and y coordinate where I assume the y coordinate is some sort of continuous function of the x coordinate. So what I'm doing right now is trying to identify all the aspects of this picture before I, use it. So right now what you see in the picture is this black curve that has 2 points labeled on it, x f of x and x plus delta x f of x plus delta x. We're going to do some analysis of the region of the string in between those 2 points. In fact, specifically, we're going to apply Newton's laws to the region between those 2 points. Okay, what else is going on? So far in my mind, I've explained that black curve in the picture, and I've explained like the labeling of the 2 points on the black line. The 2 points are arbitrary. It's just like where we're looking, but they're specifically 2 points on a curve. And since it's a curve, I think those 2 points have slightly different slopes. So what you'll also see in this picture is 2 red arrows drawn at those points. What are they're straight arrows. They are tangent lines, as you might guess, or as you can see. There's a tangent line pointing out from the first point, and it makes some angle theta 1 relative to a horizontal dotted reference line, right? Like notice, okay, notice that that red arrow going off to the left on this picture, that's a tangent line. That's the tangent to the curve at that point, x sub f of x, x comma f of x. And the angle that's being depicted there, theta 1, that is the angle between the tangent line and an imaginary or a hypothesized horizontal reference line. In other words, it's the angle that the string is making relative to equilibrium at that point, right? It's not so the angle being depicted there is between the tangent line and an imaginary reference line. It represents how steeply the string is curving or falling off at that point. Then on the other point, same thing. There's another tangent line drawn and another angle depicted, theta 2, the angle between tangent line number 2 and that point of the string. What I'm trying to emphasize right now is those 2 angles on the theta 1 and theta 2. On the one hand, they're very small. They're both very small angles because this whole thing is just a little pluck. It's just a small angular displacement occurring over a small amount of time. But even though both those angles are small, I want to say that also by a small amount, they differ. They're not the same. If they were the same, they would be like the 2 alternate interior angles, formed when parallel lines are cut by a transversal, if that is familiar from geometry. Like if those 2 angles were literally the same, that would mean, if you think about it, that the black line is diagonal. It totally is not diagonal. It's curved because someone's disturbing it. So those 2 angles are slightly different. And that is very important, you'll see in the proof. Why is it important? Because there's one other thing I have to describe, and then I'll move off the picture. The string has tension in it. Tension is the name that we give to any force of a pulling nature exerted by a one-dimensional continuous medium. Tension, like in other words, all forces obey Newton's laws. All forces ultimately have the same impact on masses, but they all have sort of but different forces have different internal features or internal properties. Like the, gravitational force is the pull exerted by planet Earth on any random object. The normal force is the pushing force exerted by one surface onto another, right? Like normal force is a push exerted by a surface, by a 2-dimensional region. A tension is not a push, it's always a pull, and it's always the pull exerted by a 1-dimensional continuous medium, like a string or a rope or a fishing line or something, okay? This is a string here. this string is being pulled at both ends by the wall. By Newton's third law, then the string is pulling on the wall at both ends. Strings exert tension. Strings experience and exert tension. Now, I don't have to use the word tension. I could just say strings exert forces. But the thing why we like the word tension is because whenever we talk about tension, we can believe two things. And this, I want you to write this down in your notes, please. And again, I'll move off the picture soon. But there's two things that we always believe to be true about tension. If there's any tension at all in a rope or in a string or in a fishing line, we can rely on two features of that tension. So here we go. So if you're putting this in your notes, which I hope you are, I'm saying properties of the tension force. Property number one, magnitude. And this is all assuming there's any tension at all. Assuming that the tension is anything non-zero, then property number one, magnitude of tension force. The magnitude of tension is uniform throughout any continuous medium, i.e. throughout any rope or any string or any fishing line. Oops, someone's here. Sorry, hold on one second. Okay, the magnitude of tension is always, like by definition of tension, this is like always you can rely on this when you're thinking about tension. The magnitude of the tension force is one constant value throughout an entire rope or throughout an entire string, throughout whatever. What I mean by that, and this is actually why we use strings, this is actually why we care about tension. What I mean by that is like again, say you and your lab partner are holding a long string. Well, if you pull on one edge of the string with 3 newtons of force, if you pull, you're on one end of the string and you pull the string to the left with 3 newtons of force. Well, first of all, by Newton's third law, that means that the string pulls you back in the opposite direction with 3 newtons of force. Now that's just Newton's third law. That's not any special property of string. But now what it turns out is if the string is pulling you to the right with 3 newtons of force, then if you look all the way throughout the whole string and all the way down to the other edge of the string, you can safely rely on the fact that on the other edge of the string, it is pulling on your lab partner with 3 newtons of force. And you can rely on the fact that that 3 newtons of force is sort of applying to every single point everywhere you are in the string. Like when you pull on your side with 3 newtons of force, what you in effect end up doing is transmitting that 3 newtons of force all the way through the string to the other side. And that's why you use strings in the first place. In other words, if you're using the string to fish, to go, to fish a fish, then the whole assumption we make, like even if we don't care about physics or know anything about physics and we just know about fishing, we just assume that if we pull up on the top edge of the rope, like with some amount of strength, we assume that the rope will pull the fish up that amount. So we pull up and we figure the fish is going to go up. And if that rope is tight at all, we absolutely would be freaked out if we saw if the rope is tight at all, then it's tight throughout. There's not going to be like some slack or some looseness in the middle of the string and then tightness for the rest. So like a string is like a force transmitter. You pull on one edge, the other edge pulls on another thing. And we act as though the string is just like an extension of our arm. And it is. Whatever force is exerted or experienced, known as tension on one end, we can rely to be the true value all the way through the string and all the way to the other end. That's in a sense what makes it a string, or that's what makes tension tension. So number one, if you know anything about the magnitude of tension anywhere in a string, then you know the magnitude of tension everywhere in the string. That's property number one of tension. The magnitude of it is a constant. It's like throughout any one given medium. But now property number two of tension, the direction of tension. I mean, remember, tension is a force. Force is a vector. Vectors have magnitude and direction. So the direction of tension is always, and this is property number two of tension, the direction of tension is always tangential to, i.e. parallel with, aligned with, along the direction of the medium itself. Okay, now again, this is like sort of obvious in a way, but it's sort of not. I'm saying whichever way the string is pointing, that's the way the tension's pointing. Again, if you pull on the top of the string and the string is like, or if you're fishing and the string is vertical, then if you pull up on the top, and then you assume that the bottom of it will pull the fish up. You don't pull up on the string and then think the string will go left. If you want to pull a string left but then have it go down, you might drape the string over a pulley or something. In fact, I guess you do in a way do that at the edge of the fishing, like yeah. But if you put a string through a pulley or something, a pulley will change the direction of a string, and the purpose of doing that is to change the direction of tension. Like when we say that a string is a force transmitter, again, we really mean it. The string is like an extension of your arm, again, in that if you bend the string, you can rely on the fact that the direction of force will bend accordingly. So what that means is if you think of tension as a vector force, it will always point along the direction of the string. It will always point tangential to it. So now, therefore, let's go back to this diagram. Okay, so that's the second property of tension. I'm saying in summary about tension in general in physics, any time you have a situation that has any tension at all, anytime you have a string or a rope or a spring, well, forget that. If you have a string or a rope or a metal rod or something that has tension in it, you can assume that the amount of the tension is the same everywhere through the rod. And you can assume that the direction of the tension is not necessarily the same as itself everywhere, but always the same as whatever the rod's doing at that place, that the tension points along the rod or the string or whatever. Therefore, in this diagram, those two red arrows that I drew, now those red arrows are vectors, right? They are straight lines drawn at tangents to the curve. Like, so they're not physical objects. They are representations. I said a minute ago that they were tangent lines. I mean, they are tangent lines, but T, therefore, also based on everything I just said, T can also just as easily stand for tension. What those red arrows really are, each of those red arrows is a vector representing the force of tension in this string at that particular point. So on the, at the original point x comma f of x, the tension in the string right there has some amount, and it's pointing in exactly the direction of the string itself, like i.e. along the tangent line to the string. It's like pointing down and to the left somewhat. And why to the left? Because remember, that whole string has to hook back somewhere to the wall that's way far away on the left. So, right, and it's just been plucked up above. So right there, that the string is like yanking it back down and to the left. On the other point, the tension arrow, the red vector arrow, is pointing up and to the right, back toward the other edge of the string. And so what we have here, and soon I'm going to turn away from the diagram, but we have here then is, I'm saying if you have a long string, it's got tension throughout all of it. You pluck it a little bit and then walk away. Well, for that one moment that you've plucked and walked away, the string now has tension throughout it, but tensions vectors that are pointing in different directions. One little piece is pulling down into the left, the other's pulling up and to the right or whatever, and yes, by the same amounts, but not in exactly the same angles, because this is a curve. Therefore, since they're not equal and opposite, like I'm saying, they are equal in magnitude, but they're not opposite direction. Therefore, they do not precisely cancel themselves out. There will be net tension on the string, pardon me. Like all of this long stuff I'm saying is to say that if you look at this picture and you look at what a string is undergoing in the moment after it's been plucked, the first thing to hopefully realize looking at those red arrows is there will be net tension on this string or within this string. And the net tension, the net tension is a net force. Net force, produces acceleration. So this string is going to accelerate, or that chunk of string is going to accelerate in a certain direction. And what we're going to find out here, what you might already guess, is it's going to accelerate back to the x-axis. So the net tension is going to act like a restoring force on this thing. And what we're going to analyze here is exactly what happens when that net force restores this chunk back to equilibrium, what kind of ripple effects or whatever it may have. That's what we're here to analyze. But Yeah, we're here to, that's why the title of this thing says, deriving the 1D wave equation from Newton's laws. We're literally just going to apply F net equals MA to that little chunk of string. And the F net is going to be the net tension coming from the string itself, restoring it to equilibrium. That's what we're going to analyze. So is there anything else in the diagram that I haven't said? So that's the nature of the diagram. Sorry. Sorry, people. Oh my God. Okay. And I realize that we only have 20 minutes. So as I said, we're going to do a lot setting this up, and then we'll churn through the mechanics of it Wednesday. It's like any other physics problem. People always say I can sort of do physics, or I can follow physics when he's doing it, but I just never know how to set up the problem, or I never know how to start. That's a common, well, yeah, the starting is the hardest part. So even if it's boring, that's what we're dealing with here. The context is we're going to pluck this string, and we're going to analyze the impact of that pluck. So I think I've said everything I need to say about the picture. So now I'm going to shift. I'm going to share a different screen now for the 20 minutes. Bear with me. Okay. So what I've said, so I'm trying to establish, so this is a derivation, this is a proof. I've established some givens here. I'm going to establish some more givens, but the first givens that I talked about the properties of tension. So these are the physics givens of this. One given is that we've got a string and it's got some tension in it. And then I'm just reminding you what tension means. So that's properties of tension, number one. Then number two now, okay, I'm talking about what's on the screen now. Number two, let's talk about this string itself. One assumption I'm going to make about the string is that it is uniformly dense. It's got a density that is constant. When I say density, I do mean, in a sense, what you mean in chemistry when you say density, but I mean something slightly broader. Like in chemistry, people say often in chemistry class, people say density equals mass times volume. Sure, I'm not disputing that. That's true. But that's an example of density. Density in general means stuff per space. It could be any kind of stuff, and it could be any kind of space. So yes, quite commonly, we're talking about how much mass we have in a three-dimensional space. We say mass per volume, we call that density. And maybe you even have an abbreviation for it in chemistry, I don't know. But in physics, you could have mass per unit space, or you could even have charge per unit space. Those are different kind of densities. And you could have any kind of space. Like for example, here, we're not really going to be working with a three-dimensional space. We're just going to look at this string, which is a one-dimensional line. And so the kind of density that's important here would be mass per unit length. All we have to deal with is length. So I'm going to define density. I'm going to define one-dimensional mass density to be interval of mass per interval of space. For every extra bit of space we look at, how much extra mass do we get? That's what I mean by density. I'm going to give it the name or the letter, the symbol mu. So I'm saying mu. So here I'm at the bottom of this page, number 2. I'm saying mu, triple equal sign. Mu is defined to be increment of mass per increment of space, of one-dimensional space, increment of length. In other words, I'm defining mu to be that. Let me pause for a second and say, this is not the mu of friction. This has nothing to do with friction. We're using the same Greek letter for a completely different thing. Sorry about that. So it's an introduction of a new concept. Mu is defined to be one-dimensional density. That's where the triple equal sign is right here. But then I'm now saying double equal sign mu naught, meaning assume for this string that the density over here is the same as the density over there. Whatever the initial density is the density everywhere. In other words, density is a constant. One-dimensional mass density is a constant. Like that, I'm not saying that's true of all strings. I'm not saying that has to be true of everything I said about tension before is true of tension in general. Now I'm saying I'm shifting to a double equal sign and saying, let's assume that we have a uniformly dense string here. So it's not like thicker over there and thinner over there or something. Okay, so that's a given for this proof that we're going to do on Wednesday. We're assuming that the one-dimensional mass density is a constant. Let me go on with some more assumptions or more givens. I'm just going to. We're also, physics-wise, we're going to assume that Newton's laws still apply, especially Newton's second law, net force equals mass times acceleration. Only now, we're not dealing with particles anymore. We're not just dealing with discrete, countable, thingy things anymore in this class now. We're now looking at a continuous medium. I don't even know how massive this whole string is, because the longer it is, the more massive it is. What I know about it is for every additional length that I give it a corresponding additional mass. I know the density of the string. So we're going to be analyzing a chunk of it, like a little stretch of string. So I just want to clarify before we go any further, we're going to apply Newton's second law to a little region, a little chunk, a little eeks. We're going to be applying Newton's law not to one point particle, one thingy thing m, but to a little stretch of m, call it delta m. And it's okay to apply Newton's laws to that as long as you're sure that the f that you're applying is like a delta f, not an f. Like if there's a whole big force applied to the whole string, but we only want to look at some little region, then only take the force that applies to that region. All right, so as long as we're consistent, we can say F net equals MA, even apply to little delta m's, as long as we consistently apply the appropriate little delta F. Okay, I don't mean to make a big deal of it, but more specifically, then I'm saying, all right, we are not going to know. I don't know what any bit of mass is. I just know that the density is constant. So from here on, whenever I'm thinking of delta m, if density, I'm here now, if density equals mass per length, then mass equals density times length. Okay, just a notational thing that I'm trying to establish. That's still physics. Now, lastly, again, I apologize. I know this is all set up, but now let me set up the math. Like, what mathematical assumptions are we going to make for this? Well, first of all, so these are the math givens now. I'm just going to triangulate. I don't know if that made any difference or not. All right, now, math-wise, we're going to assume that all of math is true, like it always is. But what couple of math assumptions do I want to highlight that we're actually going to rely on here? Well, number one, we're still going to believe what we believed in the last exam when we talk about pendulums, small angle approximation. I still believe that as long as we're measuring in radians and as long as angles are very, very small, then the sign of the angle and the angle itself are almost interchangeable, right? However you want to write it. Small angle approximation, this whole limit thing that, we've used it before, that will apply here. These are deliberately small angles that work, whether it's theta 1 or theta 2. They're slightly different, but they're both small. So we're going to assume that the small angle approximation applies to them. And then finally, just to remind you, not finally, penultimately, second to finally. Finally, let me remind you of this, and I'll go back to that page in a second. I think I'm either reminding you or I'm telling you. And I know we have 12 minutes. It's actually plenty of time for this. I want to remind you some notation here that's going to become very important. And that is, if you have any variable, call it Z for a second. Like, I know this proof is going to be about X's and Y's, but if you just picture any general variable Z, okay, whenever you see delta Z, delta anything in math or physics, delta means difference. But specifically, we use delta when what we really have in mind is perhaps a small, but a nonetheless finite difference between two values of a variable. Okay, like as in delta y means rise and delta x means run. So delta y over delta x is slope, right? The whole assumption between, so put another way, like delta y, you often write as y2 minus y1, and delta x you write as x2 minus x1. The assumption behind delta y and delta x and slope is that even if you're picking points that are really close to each other, they're still measurably far away. A delta in physics or math really means a small but finite measurable distinction between two values. That's what delta means. When we switch to D, as we do in math and physics, What we're saying is that we're still talking about a difference between two values of a given variable. But when we switch to D, we're really going to the limit. We're saying a difference between two values that's so small, it's infinitely small, right? As in, now I'll go back this page, as in, and there's like one more thing to say about this, but like the shift from deltas to D's means a shift from finite to infinitely small. So that's why we have this beast thing here that, you know, I hated the first 8,500 times I saw this in math, and I especially hated if I ever had to make sense of it or use it in a test. Like this monstrosity, but that I'm sure you recognize, the definition of the derivative, right? What it's really saying, if you really think about the notation that I'm referring you to, it's really not that much of a monstrosity. It actually really makes sense. When we say what dy over dx is really just delta y over delta x, but taken to the limit when the two values of x are so close together that they're infinitely close. Not so close that they're zero, like not so close that they're the same value, but so close that they're immeasurably close, infinitely smallly close. So what is dy over dx? In other words, like a lot of people are like, so like they hate writing dy over dx, and they just think of it as one big chunk. Like they think of it as like f prime x or something, but there's a reason we write derivatives as dy over dx, because a derivative, if you look at this definition right here, this definition, a derivative is simply a delta y over delta x, but taken to the limit as delta x approaches zero. In other words, dy dx, the derivative, is a ratio of differentials. Dy dx just means rise over run, but in a context where the run is infinitely small. I don't know if that helps anybody or not, but I'm just trying to say that this long definition of the derivative that we write is it's not a coincidence that we end up with dy over dx. We shift from deltas to d's when we shift from finitely small to infinitely small, but it still means a difference in two values. Okay. That said, and we're going to use this in the proof. That said, we have one last thing. Like, so we have delta z, if z is some variable, whether it's y or x or t or whatnot, delta means the small but finite difference between two values of that variable. Dz means the infinitely small difference between two values of that variable. And now I'm going to introduce a third piece of notation. This thing here, this may be new to some of you, and if it happens to be, if you've seen it before, great, but I'm not assuming anybody has. This little weird symbol here that looks like a lowercase delta, but it actually isn't, and it actually some Celtic symbol, I think. This thing is what we write down when it's like dz. If we write this thing, it's like saying dz. It's like a differential, but it's a little bit more specific than that. This is what we write down when we have an infinitely small difference between two values of z, but in cases for which that we know z to apply, I'm sorry, in cases where we know z to depend on more than one independent variable. We use this symbol when we're looking at differentials in a multi-varied context. So so this thing is called a partial differential. dz is a differential, like dy over dx or something. dz would be a differential. A ratio of one differential to another is called a derivative. Like dy dx is a differential over a differential. It's, in other words, an infinitely small rise over an infinitely small run. The whole package is called derivative. Okay, this thing, if you put a partial differential over another partial differential, you get a whole package called a partial derivative. It's called a partial derivative because it's a rate of change of one variable with respect to another in contexts where more other variables are involved. Okay, again, this is new, I think, to many of you. I mean, this is new, so this would be a place to like pay attention or whatever. What I'm really doing here is sneaking in our multivariable calculus because I have to. I'm not assuming you know it. I'm teaching it to you. or teaching what you need to know. Let me be a bit more specific about this, and we've got 5 minutes, and then we'll wrap up. What I'm saying is, okay, we have 3 minutes. This is the last thing I'm going to try to teach today, but I'm not going to go over, I don't think, but I'm going to do one more page of this to try to make this as clear as I can. So this is like a new math concept, just like we had to know something about differential equations to do stuff. We have to know this concept to do stuff. So I'm going to write it more clearly on the next page. I'm adding one line and recopying, but it's the same thing on the next page. I'm saying, and this is where we'll pick up on Wednesday, of course, but okay, what I'm just saying here is I'm saying if you have some dependent variable that depends on more than one independent variable, now that's a big if. I mean, That's never that I'm not assuming you've ever seen that. It's never happened before in physics in your education, and it's never happened before in any math class you've taken, unless you happen to have taken a math class called multivariable calculus or something. Okay, but this is a new thing. But I'm saying, imagine that you have, and I know it's 4:20, so I'm just going to like say it once and then we're gone. And I apologize, and we'll pick up Wednesday. But I'm saying, if one variable depends on more than one thing at the same time, as in lab 3, as in the height of the string depends on where you're looking at the string, but also depends on what time you're looking, right? The height of the string depends on X coordinate, or the Y position of the string depends on X position, as well as depending on time. And it depends on each, like, independently. That's how in lab 3, you were able to make both a movie of one slice of the string, but also you were able to take a snapshot of the whole thing, right? Whenever that occurs, if you were thinking of graphs or whatever, you ever want to think, oh, like, how quickly is the Y value of this function changing? Well, it depends on how quickly that one independent value is changing, and it also depends on how quickly the other is. So what we're saying here is, if you had a normal everyday single valued function, the rise, so in a normal single valued function where there's just rise and run, the rise equals the rise per run times run. Like, it's so obvious, like you wouldn't even bother to say it. The rise equals rise per run times run. In other words, rise equal, the infinitesimal rise would equal derivative times infinitesimal run. I mean, just multiply both sides by dx, right? Well, the same thing is going to be true if something is depending on more than one independent variable. The whole is going to, excuse me, be equal to the sum of its parts. So if you want to know how much the string is rising a little bit at some moment in lab 3, well, that's going to depend on the rate at which it rises per where you're looking, plus the rate at which it rises per what time it is. Dy will equal the partial derivative of y with respect to x times infinitesimal x, plus the partial rate at which it depends on time times time. The whole is equal to the sum of its parts. But I'm just going to end there. So we now have 3 types of differences. We have small but finite differences called delta. We have infinitely small differences, d, and we call those differentials. And then we have infinitely small differences in multivariable contexts, and we call those partial differentials. If something is depending on 2 variables, then there's a rate at which it fluctuates depending on one, and there's a separate rate at which it fluctuates on the other. Each of those separate, individuated, distinct rates we call partial rates or partial derivatives, and we use this crazy symbol, this thing that looks like a delta, looks like a lowercase delta, in order to signify it. But there's no name for that symbol at all. It's always just read as partial. So we just say like partial y, partial x, or whatever. There's no other name for it. But I know it's 4:23. I'm so sorry. I'm just going to go. I'm not even going to say, I mean, goodbye. Sorry if there's questions asked on Wednesday. I owe you work. You owe me nothing. Thank you very much. Thank you, Farida. Totally appreciate it. Thank you all. I'm going to hit end before the other people will come in. But thank you. And I'll post the blah, 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 and blah, 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 and Cork, bless America, and blah, blah, blah. Have a great day, you too. Thank you, guys. Okay.